In this unit, we'll discuss normalized numbers in base 2, and that'll provide a lot of motivation for how the double number system was designed. A normalized binary number is written in the following manner displayed right there. Only one digit to the left of the decimal point, and the value of that digit, D0, is always 1. That's where the term normalized comes from. And then again, the exponent e is an integer. So normalized binary numbers are always of the form, here I've got one with a 6-digit fraction, of a leading 1, the decimal point, then the fraction bits, and then it's a floating point number, multiplication by 2 raised to the exponent, and the exponent is restricted to be an integer. Clearly, if a number is known a priori to be normalized, then there's no need or reason to store or transmit the D0 digit, since it's already known to be 1. Finally, there's a plus or minus sign in front to denote positive or negative, giving, for example, this as the form of a normalized binary number: a sign, a leading 1, a fraction, and an exponent. How do we store such a representation? Clearly, you need 1 bit to store the sign, perhaps 0 positive, 1 means negative. The fraction needs to be stored bit by bit. Here it was a 6-digit fraction, so that would require 6 bits. Remember, since this is binary, the digits of the fraction are 0 or 1. Don't bother storing D0. Lastly, store the integer exponent with a binary representation. A good question is, what about the sign of the exponent? Should this binary representation be a signed binary representation or an unsigned? We'll discuss that later. For the next 2 slides, we want to see exactly how the number of bits that are used to store the fraction controls the precision to which numbers can be represented, and the number of bits used to store the exponent, which will determine the range of values that e can take on, well, that controls the range of numbers from smallest to biggest that can be represented. Let's see this. Let's look at the distribution of normalized numbers with 3 digits in the fraction. We'll start with what I'm calling the fundamental interval, where e equals 0. Since there's 3 digits, this really ends up being 8 evenly spaced numbers from 1, that's with all the digits in the fraction equal to 0, to 1 7/8, that's with all the digits in the fraction equal to 1. So 8 evenly spaced numbers from 1 to 1 7/8. With e equal to 1, the 2 to the e term doubles everything, and it leads to 8 evenly spaced numbers from 2 to 3 3/4. Note, this line is not evenly spaced. The spacing between the numbers in the interval 1 to 2 and the spacing between the numbers in the interval 2 to 4 are different by a factor of 2. Likewise, with e equal to -1, this leads to 8 evenly spaced numbers starting at a half and going up to just less than 1. Continuing on, e equal -2, the numbers begin at a quarter, they go to a half, and it's 8 evenly spaced numbers in that range. At e equal 2, it gets 8 evenly spaced numbers from 4 to 7.5. At e equal -3, it's 8 evenly spaced numbers from an eighth to a quarter. This goes on indefinitely. It's just limited by the range of values that e can take on. The number of bits used to represent e, which dictates e's range, dictates the range of numbers that can be represented. What about the precision? In this example, there were 3 digits in the fraction. Let's look and see how this changes if there are k digits in the fraction. Remember, with 3 digits, all the intervals have 8 evenly spaced numbers. If there are k digits in the fraction, then those switch to 2 to the k evenly spaced numbers, and the spacing in the interval 1 to 2 changes from 1/8 to 2 to the -k. Moving over one interval, there's still 2 to the k evenly spaced numbers, and the spacing is twice as large. Going the other direction, there's still 2 to the k evenly spaced numbers, and the spacing drops again by a factor of 2. So here it's clear that the number of digits in the fraction controls the precision to which numbers can be represented. I want to bring your attention to the bottom comment. This line is not evenly spaced. In each of the colored intervals, I've drawn the spacing equal, but remember that the colored intervals are of different lengths. As you move to the right, the length of the colored intervals doubles. As you move to the left, the length of the colored intervals halves. So this line is not evenly spaced. Let's look at the actual spacing of normalized numbers. Here are three of the intervals: the interval 1 to 2, the interval 1/2 to 1, and the interval 1/4 to 1/2. For 3 digits anyway, that shows the actual spacing. This line is spaced evenly. This is a very natural idea. Make the spacing between the numbers proportional to the magnitude of the number. It gives the same relative accuracy across the entire number line, another interpretation of the word normalized. And actually, just remember, the spacing doesn't really change proportionally with the magnitude of the number. It only changes abruptly at every power of 2. How do unnormalized numbers get included? Let's look and see the process as we have the intervals. There's the fundamental interval, written as 1.f. That takes us from 1 to just less than 2. Next, include the first halving of that interval, in other words, e = -1. This is the remaining gap to get down to 0. In order to close that gap, do another halving, e = -2. Here are the numbers that are added with e = -2. It's getting closer to 0, and there's the gap. But what you notice is that the gap to 0 is as large as the interval that was just added. So in a relative sense, we're not getting any closer to 0. We add an interval with a lot of precision, and the gap to 0 is as large as the interval that's just been added. We'll never make it to 0 this way, since preserving the relative spacing means that always we're only half as close as we were in the previous step. Moreover, the spacing is getting half as large, so from a relative point of view, we're not making any progress. At some point, just stop making the spacing smaller. Maintain the current spacing, and another copy of this interval will go all the way to 0. That last group of numbers is called the unnormalized numbers. Here I've drawn them going from 1/4 to 0. Notice that they have the same spacing as the spacing from 1/4 to 1/2. In the single and double number systems, this unnormalized step happens after several halvings, not just 2. On this slide, all the numbers from the double number system are shown, as we learned about earlier. Let's introduce some terminology. Float x is the closest representable number to the real number x. That was also called Rx earlier. Real min is the smallest positive normalized number. It's not the smallest positive number, but the smallest normalized positive number. Right here we can see that's 2 to the -1022 power. Real max is the largest positive normalized number. That's shown on the right-hand side. It's less than 2 to the 1024th by 2 to the 971. And finally, eps of r is the distance between a representable number r and the next representable number. These are marked across the top. For all the intervals except the unnormalized interval, the distance between numbers increases proportionally by a factor of 2 as you move from one interval to the next. This distance is always a power of 2, and it's called eps. Eps of 1, in this case 2 to the -52, is often called the machine epsilon. But eps really is a function of the number.